Welcome to the deep dive. Have you ever just felt completely overwhelmed by a huge project? Maybe a pile of work tasks, some complex research, or even, just planning a big trip. Well, this deep dive is definitely for you. We're not talking about just grinding harder, we're aiming for thinking smarter. Today, we're exploring computational thinking, or CT. Think of it as like the best possible operating system upgrade for your brain. We've gathered quite a few sources, and they interestingly treat CT not just as a coding thing, but as a really structured way to solve problems.
Clearly, so effectively that people or computers can use them.
Okay, so it's a framework, and while it feels super relevant now, you're saying it's not exactly brand new, is it?
No, not at all. The term and the concept were really popularized back in 2006. That was by Jeanette Wing. She's a distinguished computer science professor, was at Carnegie Mellon. Actively tackle complex stuff. So by learning these pillars consciously, we're just optimizing our natural instincts, sharpening the tools we already possess.
So we're kind of formalizing our best cognitive habits, making them conscious. And if we can apply these four pillars deliberately, it's like a shortcut to better, maybe faster decision-making.
Precisely. They provide the scaffolding, you could say, for effective problem solving, whether it's a personal issue or a complex project.
All right, let's jump into the first two pillars then. These seem to be about handling the scope of a problem, right? Breaking things down and then figuring out the instructions for those pieces. Let's kick off with pillar one, decomposition. So taking that massive, overwhelming problem and slicing it into smaller, simpler, more manageable parts. My question here is, how do you know when to stop? Do you just keep slicing until everything's microscopic?
That's a really good question. And no, the goal isn't like atomic level detail. It's about manageability. Think of decomposition as an anxiety reducer, actually. You break the big scary thing down until each little piece feels doable, solvable. Our sources use great examples. Planning a birthday party seems huge, right? But your brain doesn't just freeze. It naturally starts decomposing. Okay, order the cake, decide on the guest list, buy the gifts. Suddenly, each of those smaller tasks feels executable.
That makes total sense. It reframes the monster project into just a list of smaller achievable things, like baking a cake. The overall task, bake a cake, feels big, but prepare ingredients, mix batter, bake, decorate, those are steps I can handle. Okay, so once we've decomposed, broken it down, we need the instructions for those smaller pieces. Which brings us neatly to pillar two, algorithm.
Right. An algorithm is all about efficiency. It's just a series of clear, sequential steps or rules designed to solve the specific problem. It's the recipe, the definite recipe. And the key word there, absolutely, is sequential. The steps have to be followed exactly in the right order to guarantee you get the outcome you want.
And we use these constantly without thinking, don't we? Like making instant noodles. I definitely have an algorithm for that. Boil water, put noodles in, wait till cooked, add the seasoning packet, stir, serve. Done.
Exactly. And I bet if you skip the stir step, the result wouldn't be quite right, would it? Because the algorithm wasn't followed precisely. That's the core principle. Your brain actually stores thousands of these little algorithms for driving, walking, making coffee to free up your conscious attention for trickier things.
That's fascinating. So we move from managing the sheer size of a problem with decomposition to maximizing the efficiency of solving the pieces with algorithm. Okay, let's tackle the last two pillars. These feel more about finding leverage, identifying the important bits. Pillar three is pattern recognition. So finding similarities or recurring trends in those pieces we broke down earlier. How does the brain know what's a useful pattern versus just random coincidence?
Well, the brain is fundamentally a prediction machine, and pattern recognition is its engine for prediction. If you spot a pattern, you don't waste energy figuring things out from scratch. You can apply a solution that worked before for a similar situation. Our brains are constantly scanning for these predictable sequences. Like you see dark, low clouds gathering. That pattern predicts rain, so you grab an umbrella. It's an instant, efficient mental shortcut based on past experience. Or think structurally, maybe like a school schedule or a work routine. If you notice that, say, art and sports are always on Friday afternoons, recognizing that pattern helps you plan your week more efficiently, right? You know what to expect.
Okay, got it. Now for the pillar that honestly sometimes feels the most challenging, maybe the most powerful, abstraction. My immediate thought is, isn't deliberately ignoring details kind of risky? How is this different from just being lazy or putting things off?
That's probably the most crucial distinction to make. Abstraction isn't about ignoring details because you can't be bothered. It's about deliberately and strategically filtering out irrelevant information. You consciously decide to focus only on the most essential core features of the problem. It's the absolute key skill for managing cognitive load. Think about it. If you don't abstract, Your brain gets completely bogged down in noise, in irrelevant data. But if you can strip away the distractions and focus on the main variables, you suddenly see the underlying structure of the problem much more clearly.
Right, and this is where it gets really practical. The driving example from our sources is perfect. When you're driving, your brain cannot possibly track every single detail. Every wheel rotation, the brand of the car next to you, how many trees are on the side of the road, that's all just noise. Your brain abstracts. It focuses only on the critical stuff. Destination, main route, immediate hazards like brake lights or pedestrians.
Exactly, and that ability to simplify complexity, to essentially throw away the unnecessary data points, is what lets your brain operate at a higher, more strategic level. It's about deciding where to put your limited mental energy. Abstraction is, in a way, freedom from information overload.
Okay, so we've laid out the 4 pillars: decomposition, algorithm, pattern recognition, and abstraction. Powerful ideas. But how do we actually, practice them? Let's look at how the sources suggest these get trained through some practical activities, not just in coding, but across different areas.
Good idea. Let's start with a real classic science activity, planting beans. This uses decomposition and algorithm right away.
Right. You have the step-by-step process. Get the pot, add soil, make a little hole, put the seed in, cover it, water it, put it in the sun. That's the algorithm. And if you skip a step, like watering, the algorithm fails. The bean probably won't grow.
But the real CT magic happens when you bring in abstraction and pattern recognition. The learner uses abstraction by focusing only on the essential rule. Plants need water and sunlight to grow. That's the core principle. They have to learn to ignore the noise, the specific brand of soil, the exact color of the bean, the shape of the pot. Those details are irrelevant to the fundamental need for water and sun.
And the pattern recognition part is seeing the predictable life cycle, isn't it? Seed becomes a small plant, which grows into a larger plant. Recognizing that basic pattern means you can anticipate what the plant will need next. Okay, let's switch gears. How about something more related to numeracy or even coding, like training a cheerful robot?
Yes, that's a fantastic one for drilling algorithm development. The learner has to give very specific sequential commands, often using instruction cards. Move forward, turn right, maybe pick up. The focus here has to be entirely on the correct sequence. If you want the robot to move, say, 3 steps forward, you need 3 move forward cards in exactly that order. Speed isn't the issue, the sequence is.
And I imagine kids doing this quickly stumble into pattern recognition, right? If the robot needs to move in a square shape, they'll quickly spot the repeating pattern, like go forward, turn right, go forward, turn right.
Exactly. Recognizing that repeated sequence lets them build the algorithm much faster. They don't have to reinvent each side of the square. And finally, we can see CT applied in classification tasks, like setting up a smart sorting machine for waste, sorting things into organic versus anorganic, for example.
This sounds heavily reliant on abstraction. The machine or the person programming it has to focus only on the key defining feature of the material, yeah. They have to ignore things like the item's color, its specific shape, maybe even its smell. Those are irrelevant details for this task.
Precisely. Abstraction provides the core sorting rule. Where did this material come from? Was it from nature or is it man-made? And that simple rule, born from abstraction, directly enables the pattern recognition. Organic materials, stuff from nature like food scraps, leaves, they follow the pattern of decomposition.
Hatur nuhun, selesai.
Thank you.